This is Design Group 22's rocket video. Our first aim being to be able to launch a water rocket housing an egg. Next being able to keep the egg in the longest possible flight time. To be able to sustain various uncontrolled factors, as well as to make sure the egg does not break. Lastly, I'd like to talk about propulsion. So the rocket propulsion system follows the laws laid out by Isaac Newton, his third law to be exact. Newton's third law states that for every action force there will be an equal and opposite reaction force. Our action force comes from the water being expelled out of the nozzle, which itself is accelerated by expanding air, and in turn our rocket accelerates in the opposite direction. A breakdown of the thrust can be shown using a spreadsheet in which you can change many variables to achieve an optimal design. Within our spreadsheet, we can have a look at impulse, which refers to the change of momentum of the rocket when force is acting on our rocket. The impulse is also inversely proportional to the water volume fraction over the duration of time, which can also be seen on the spreadsheet.
With the help of simulation software, we can optimize a rocket to meet the design criteria by making adjustments to the fin position, shape, and number of fins along with the shape of the nose cone. It is important to have a stable rocket to ensure the rocket has both a controlled climb and descent. Making changes to these parameters help you to make an informed decision and make multiple versions of your rocket, each better than the last.
Now I'd like to talk about the parachute system, with one of the objectives and maximum flight time, and as such, the parachute system is equally as important to optimize. The cross-sectional area of the parachute will play a key role in the descent time. Again, with the use of both Excel and simulation, we can tweak the design of our rocket and go through many iterations of the rocket to find the best ratio. With deceleration being one of the most critical for the egg's safety, it is important to strike a balance between deceleration and force. Finally, I'd like to talk about the integrated design. The size of the rocket or volume will have an effect on the launch of the rocket. We've considered a 2-litre bottle for this launch. The volume of the rocket will determine the maximum amount of energy which can be stored in the compressed gas, but also being aware of how much pressure we are dealing with. The lower the weight of the rocket, the better it will fly. The less weight it has, the more aerodynamically stable the rocket can be to produce a good flight trajectory. And a good flight trajectory needs to be maintained because the rocket needs to land in the designated area. Having a center of mass forward will keep it more stable. This is where the fin position and the size has to be considered in order for the best position of center of mass. The nose cone will be required to be as streamlined as possible because this feature will cut through the air first, and the nose cone will also hold the parachute. To conclude, during our project we had learned a lot while designing our rocket. During our integrated design phase, we looked into the aerodynamics and center of masses and how they have an effect on the flight time of the rocket. We also learned about the positioning, length and the number of fins, and how they all have a significant impact on the rocket's flight as it controls both direction and stability, but also having an effect on the rocket's center of mass and how much drag it faces when it flies. Unity was also an excellent tool to analyze the different designs, as it allowed us to change variables and make adjustments quickly and test them on the simulation. Thank you for listening.